When modeling in Kامسول multiphysics, there are two ways to finalize your geometry: form union and form assembly. Form union is the default option and is suitable for most cases. However, form assembly can be a helpful alternative for specific cases, listed here. This video will discuss and exemplify the differences between the two finalization methods. If you are only interested in the application of form assembly, follow the links below. In Kامسول multiphysics, when modeling a geometry with multiple objects, we need to look at how we bring this collection of objects together and how it affects our modeling strategy. There are three main aspects that distinguish these two operations from each other. The first being the geometrical representation of your model geometry and how it is partitioned differently with the use of either method. Consequently, how the geometry is represented will affect the mesh of the model's geometry. The mesh needs to connect the separate objects within our model. Since the mesh and physics are related, this will affect the physics of our model and hence the solution. Let's start with discussing the general geometry and mesh differences in detail. Here we've imported the assembly of a reciprocating engine. In the selection list window, we can see a list of all of the solid objects like the connecting rods, pistons, cylinders, everything that makes up this assembly. This geometry needs to be brought together into a composite object before meshing. The form union, form assembly node determines how the software treats a collection of objects in a geometry. To illustrate these concepts and see how these separate objects are dealt with, let's move to a simple 2D geometry. This geometry contains two objects, both rectangles, that are touching on one side. And let's go ahead and toggle on the geometry labels to see those. When we use the form union or form assembly method, our collection of objects, here these two rectangles, become regions which we call domains of a composite object. First, let's finalize the geometry using form union. You can see we have a single object consisting of two domains and 9 edges. You can see that this edge is a shared edge between the two domains, and we have these two short edges adjacent to it on both sides. If we change this to form assembly, I still have a single object consisting of two domains, but now there are 8 edges. The two edges that are touching are completely separated. There is no shared edge or shorter edges as a result. So when using form union, you can think of the objects as bonded together. The neighboring domains are connected through shared boundaries. Using form assembly treats our geometry objects as separate entities, much like the parts of an assembly. The resulting domains are thus disconnected and do not share boundaries with their neighbors. Now let's look at the changes in how the geometry is meshed after using both methods. I'm going to start this off with form union and edit the default meshing sequence to define an extra fine mesh in one of the domains. You'll see that our geometry exhibits a continuous mesh across all domains. At the shared boundary, the mesh is growing to accommodate the different mesh sizes for both domains. If I move this rectangle up, making these shorter edges more pronounced, you can see that the constraint of a continuous mesh results in a finer mesh close to the short edges. So using form union can result in small features in your geometry when there is misalignment between two objects, like we see here. There are a few approaches we could take to deal with misalignment such as this: moving the objects so that they are aligned, performing virtual operations on the geometry, or forming an assembly of the geometry. Let's see how the mesh differs if we form an assembly. Here the two domains are meshed completely independently of each other. according to the previously defined mesh settings. We can call this a disconnected mesh since the two domains are disconnected. To ensure continuity across boundaries, these two edges are connected through identity pairs, which are automatically set up for all touching boundaries. You can also use contact pairs for simulations involving structural contact between the objects. Identity pairs are operators that map variables from one boundary to another. If I zoom into the edge separating the two domains, you can see the mesh elements and nodes do not match up. If we have any misalignment wherein the mesh nodes and elements do not correspond to each other in the boundary, then we call this an incompatible mesh. An incompatible mesh on touching boundaries is acceptable for some cases and can also be resolved for others. These specific cases, as mentioned before, are approached differently with respect to defining the physics. For instance, returning back to our original geometry of the reciprocating engine, a multi-body dynamics model, form assembly is used. Prismatic and hinge joints allow translational and rotational movement of these separate domains. Had we used form union to finalize this geometry, these domains would be bonded together and unable to move. For more information on this and the other use cases of form assembly, please follow the links in the description.